Hi, in the last tutorial we discussed a simple way to make edge detection. I have to say that I made a mistake. You can add 1.0 to the pixel position because in the UV scale that means adding 100 of the image size. The right approach is to add the size of the pixel on the screen in terms of the UV coordinates. We're using the constant screen pixel size. Anyway, as I mentioned before, this is not the right way to do that. We have to use a convolution matrix, and that's what we're going to do now. The convolution matrix consists of the multiplication of the color of the pixels surrounding the current pixel and then add them together, and that's it. Using this pixel as an example, the convolution matrix or kernel will take the colors of the surrounding pixels, including the color of the center pixel, multiplies each value by a factor and then adds them together. The value of the factor depends on the effect we want to obtain. You can find some examples of kernels for different effects on Wikipedia. You might notice that some of them multiply by an additional factor. This is obviously to normalize the color vector, which has to be in a certain range. Also, you might notice that the size of the kernel will vary as well. This animation shows you the calculation process with the kernel or convolution matrix. The algorithm used to calculate this is also shown here, but in the case of the shaders, it is not necessary to make loops because it's done by default. The code that we're going to use is on the GODOT website. As you can see, it first multiplied by a value of -8. It's an odd way to normalize the vector, because doing that in the remaining vector sums, we're going to get a vector of size between 0 and 1 for sure. Here is a nice overview about the filter that we will apply in our shader. Basically, it describes the process that we just covered by talking about the kernel, the multiplication by a factor, and the addition of the results of this multiplication in the surrounding pixels. So I am just going to copy the code into a new shader to show the result of the edge detection effect using the convolution matrix. Just make a new shader and copy, and there you have it. As you can see, the output is much different from the previous results. Many more effects can be achieved using this approach. On GODOT Shader's website, we have the color blending modes. Normally, we use the mix function to make a linear interpolation, but if we want to get results similar to image editing programs, we have to use these functions. At the bottom, we have the functions ready to use in GODOT. So let's try some of them. I encourage you to experiment with the rest by yourself. So what I'm going to do is create a new shader and then declare a variable to import an image to test the blending modes with. After that, I am going to declare two more variables inside the fragment function to do the color mixing. Then we just set the output to the A variable. Now I'm going to attach an image to the uniform variable that I created before. I'm going to select the default GODOT icon, and with that I am going to do the blending. Now I am just going to copy the blending functions from the GODOT shaders page, and now let's try some of them. For example, we go multiply, you can see the effect, screen, darken, lighten, and difference. Finally, we're going to use some linear algebra to produce a color effect, the Sephia color. The code that we're going to use is simple. It's just a matrix that we will use to multiply all the color vectors of our image. You notice the matrix that we're going to use is composed of three vectors that define the three dimensions of the RGB color space. This concept is important because the idea of transformations is that we can modify all the dimensions of the matrix to get the result that we want. In this example, I have three objects. They represent the RGB color space. The object on the left represents the RGB space without modifications. And the middle one represents the transformed RGB space. In this case, what I want is to limit the space of the color vectors to a smaller one where the sepia tones are located. Let's suppose that in this area the sepia colors are found. The cube on the right represents the output of result of applying the transformation to the color vectors. I am not going to use linear transformation as such. I am simply going to modify the vectors that are inside the matrix at my convenience. These vectors are called basis vectors. GODOT shows the transformation matrix of the objects. Inside are the basis vectors in horizontal form. XYZ or RGB in the case of the RGB color space. For example, I can scale the object on different axes if I change the size of the base vectors. What I'm going to do is to move the base vectors y and z to the right on the x-axis. First I move the y vector, one position in the x-axis, and then I am going to move the base vector z in the x-axis. The last demonstration serves to know what's happening, the transformation of the RGB space in the shader. The difference being that I am using a 3x3 matrix because in the RGB color space there is no position, but there is a dimension A that has to do with opacity. So I am just extracting the RGB vector and multiplying it by the 3x3 transformation matrix. Now I am just going to apply the shader to the paper container to get the result of the Sephia filter, and there you have it.